The limitations of carbon-13 NMR that we've discussed make it clear that you can get very little connectivity information out of a pure carbon-13 NMR spectrum. Because of this, a few different techniques have come up to give us more information from carbon-13 NMR, and the most important and useful of these is called distortionless enhancement by polarization transfer, or DEPT. We're not going to talk about the underlying physics of DEPT at all because it's rather complicated. Instead, we're going to focus on how DEPT gives us useful information about the number of hydrogens connected to a particular carbon atom. From a series of DEPT spectra, we can determine whether a carbon has 1, 2, 3, or even no hydrogens connected to it. In a language of classifying by substitution pattern, a primary carbon bears 3 hydrogens. In other words, it's a CH3 group. A secondary carbon, or methylene, is a CH2. A tertiary carbon, or methine, is a CH, and a quaternary carbon is just C without any hydrogens. What the DEPT experiment does is give us a series of spectra. So there are multiple carbon-13 NMR spectra in a DEPT experiment in which the different carbon-13 signals are transformed in accordance with the number of hydrogens that they have attached. The numbers here we can understand as an excitation angle for the hydrogens. And so this is 0 degrees, 45 degrees, 90 degrees, and 135 degrees, and different things happen depending on the excitation angle. The 0 degree, quote-unquote, hydrogen pulse just corresponds to a regular carbon-13 NMR spectrum, since we're not really doing anything special. In the 45 degree case, we display peaks only for the primary, secondary, and tertiary carbons. No signals for quaternary carbons are shown. From this information, we can look at the original carbon-13 NMR spectrum and see what appears to identify quaternary carbons right off the bat. And so immediately, since this peak disappeared in the 45 degree spectrum, we can identify this as a quaternary carbon, which I'll just label C. The 90 degree spectrum shows us CH resonances only. So from this spectrum, we can immediately identify CH resonances. So we now have 3 methine peaks that we've identified. The 135 degree case is interesting in that CH and CH3 peaks are shown with the normal polarity, in other words pointing upwards or positive, whereas CH2 peaks have inverted polarity, which means their peaks are pointing negative. That's actually a bit interesting to think about in terms of the frequency spectrum and Fourier transform. What does a negative frequency component mean? But we're going to leave that aside for the time being and just use this to our advantage to identify, for example, that this negative peak in the 135 degree spectrum must correspond to a CH2. And using process of elimination, since we already identified the methine peaks from the 90 degree case, we can conclude that anything that's left unassigned must be a CH3. And just to summarize, in the language of substitution pattern, we would say that this carbon is quaternary. These carbons are each tertiary, or methines. This carbon is a methylene, or secondary. And this carbon is primary, or a methyl group. Here's the molecular structure of the compound that corresponds to this DEPT spectrum. And the DEPT information actually helps us make assignments in this case greatly. For example, we can notice that there's only one quaternary carbon, one carbon bearing no hydrogens in this structure, and it's this one highlighted in blue. I really love this example because it highlights the issue from the first video of this series of symmetry and stereotopic relationships. For example, these 2 methylenes highlighted in black should be equivalent by symmetry since they're related by a rotational axis of symmetry in the molecule, and this is the CH2, the secondary carbon peak, corresponds to both of these carbons highlighted in black. Both of the methyls highlighted here in purple correspond to the single primary or methyl peak in the carbon-13 NMR spectrum. And 2 pairs of the aromatic carbons are also related by symmetry, by a rotational axis. And so the 2 highlighted in red, which are both CHs, or methine protons, correspond to one of the 3 methine peaks. These highlighted in green correspond to one of the other methine peaks, and this one highlighted in yellow corresponds to the last methine peak. And so the DEPT approach, as we see here, really helps us assign carbons to different resonances within the carbon-13 NMR spectrum by giving us information about how many hydrogens each carbon has attached to it.